11 years ago, I made a video where I extended the concept of writing numbers in whole number bases to writing numbers in fractional bases as well. This enabled me to write numbers with fractional digits, not just whole number digits. Here is a picture of the numbers 1 through 10 written in base 2, step 1/2. Now I would like to do something similar today. I would like to extend modular arithmetic to where the modulus can vary. But first, I'd like to travel back in time, back to what I looked like 11 years ago, as I go through the rest of this video. Traditional modular arithmetic, the kind Gauss invented, is based on remainders left over after division. For instance, if we take 12 and divide it by 5, and we take 17 and divide it by 5, we are left with a remainder of 2 in each instance. Since they have the same remainder, we say that they are congruent with respect to the divisor of 5. We call the divisor a modulus, and sometimes abbreviate it mod. We can also think of these points as being on a number line, where there is a consistent distance gap between congruent numbers. To have a variable modulus, we need to make this gap shrink or extend, or perhaps do both. One way to make an extending gap is to first choose an arbitrary point on the number line, like the number 5, and then make the gaps larger as we increase our distance from this point. I will call this point an anchor point. 5 is the anchor point we'll use in this example. Here, we're choosing the length of this gap to be determined by 2n, where n is the number of iterations until the next point congruent to the anchor point is reached. This is a gap that is constantly increasing. This chart shows that the first gap has length 2, the second length 4, and so on. Going by the directions indicated in this chart, we see that the anchor point 5 is congruent to 3 and 7 with the first iteration of 2n, -1 and 11 with the second iteration of 2n, and -7 and 17 with the third iteration of 2n. Now here's the tricky part. How can we tell what numbers in between these defined congruent points are also congruent? Going back to a traditional modular arithmetic problem, we see that 17 is congruent to 12 mod 5. Now instead of considering remainders this time, let's consider the distance the points 17 and 12 are from the points congruent to 0. Both 17 and 12 are 2 points distant from a point congruent to 0. So rather than saying they have a remainder of 2 that makes them congruent, we can say each is 2/5 of the distance between 2 points congruent to 0, and use that as a definition of congruency. So if we take the fraction 2/5 and apply it to a particular region with an upper and lower bound congruent to 0, we just multiply the 2/5 times the length of the region and add that on to the lower bound of the region. That will always give us points that are congruent to each other when the modulus is constant. In particular, it will give us points that are a distance of 2 away from the lower bound of a region where the modulus is constantly 5. The only modification we have to make to this strategy when our modulus varies is that we consider upper and lower bounds congruent to the anchor point instead of congruent to 0. But otherwise, the thought process is the same. In our example of modulus 2n with anchor point 5, we find that 13.4 is congruent to 8.6 in this case. Visually, we can sort of see how these points are 2/5 of the distance between points congruent to the anchor point here. Notice how decimal congruencies begin to appear. This is evidence that our extension of modular arithmetic is a lot freer than the standard modular arithmetic. In standard modular arithmetic, we use the fraction 2/5 in our example, but we could have taken any fraction with a whole number numerator and 5 as the denominator. In extended modular arithmetic with a variable modulus, we have a lot more choices. We can pretty much choose any fraction we want. We can also choose any anchor point we want. Our main limitation is how we want our modulus to vary. I imagine we'd want to keep each distance from each iteration as a number above 0 until we have a better idea of what we're dealing with. You probably are familiar with how modular arithmetic is similar to going in a circle, and indeed it is. That's a good visual for modular arithmetic, I think. Now with a variable modulus, the circle changes size, depending on the distance between points congruent to the anchor point. I think the only thing left now is to consider the notation. Really, the addition of the anchor point is the only major change, so I'd just put it in brackets, abbreviate it with A, and tag it on to the end of the equation after the mod part. One interesting thing about modular arithmetic is after Gauss created it, he was almost immediately able to use it to solve an old problem from antiquity regarding constructible polygons. But I can't think of a single application for this particular extension of modular arithmetic. It's a classic example of pure math. Not useful in the slightest, but it doesn't matter. Still fun to do anyway.